Welcome back to our course, Fundamentals of Operating Systems, based on the textbook Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter Galvin, published by Wiley Publishing. We have been discussing in this unit process synchronization. And in the last lesson, we were introduced to the topic of the critical region or critical section. This is an area where more than one process can be working concurrently. And when you have two processes working concurrently in the same general area, whether that be program or data, you know we have a recipe for a problem. Now in this lesson, we're going to start talking about some of the ways of dealing with the critical region, starting with one called the test and set. So let's continue. Many modern computer systems provide special hardware instructions that allow us to test and modify the contents of a word or swap the contents of two words atomically. A word, as used here, is the natural unit of data used by a processor design. My children's first Nintendo used an 8-bit word. When we bought a new Super Nintendo, it used a 16-bit word. And of course, you can imagine what the word size would have been on our next Nintendo 64. And by atomically, I mean as one interruptible unit. In other words, the content can be changed in one action. We can use these special instructions to solve the critical section problem in a pretty simple manner. Rather than discussing one specific instruction for one specific machines, the authors abstract the main concepts behind these types of instructions by describing the test and set instructions. The test and set instruction can be defined as you see here. The important characteristic of these instructions is that they are executed atomically. Therefore, if two test and set instructions are executed simultaneously, each on a different core, they will be executed sequentially in some arbitrary manner. If the machine supports the test and set instruction, then we can implement mutual exclusion by declaring a Boolean variable lock initialized to false. The structure of a process is shown here. The hardware-based solutions to the critical section problems are complicated as well as generally inaccessible to application programmers. Operating system designers build higher-level software tools to solve the critical section problem. The simplest of these tools is the Mutex Lock. In fact, the term Mutex is short for mutual exclusion. We use the Mutex Lock to protect critical sections and therefore prevent race conditions. That is, a process must acquire the lock before entering a critical section. It releases the lock when it exits the critical section. The acquire function acquires the lock and the release function releases the lock as shown at the top of this slide. A Mutex lock has a Boolean value whose value indicates if the lock is available or not. If the lock is available, a call to acquire succeeds, and the lock is then considered unavailable. A process that attempts to acquire an unavailable lock is blocked until the lock is released. The definition of acquire is shown at the top of the slide, followed by the definition of release. Calls to either acquire or release must be performed atomically. Therefore, Mutex locks can be implemented using a lock implemented in hardware. Remember we said atomically means as one complete action. In other words, it calls for the lock and then makes it available in one step. The main advantage of the information given here is that it requires busy waiting. While a process is in its critical section, any other process that tries to enter its critical section must loop continuously in the call to acquire. This continual looping is clearly a problem in a multi-programming system where a single CPU core is shared by many processes. Busy waiting also wastes CPU cycles that some other process might be able to use productively. In other words, the continuous looping is wasting cycles. The type of mutex lock we've been describing is also called a spin lock because the process spins while waiting for the lock to become available. Spin locks do have an advantage though, in that no context switch is required when a process must wait on a lock, and as we've already discovered, a context switch may take some time. In certain circumstances on multi-core systems, spin locks are in fact the preferable choice for locking. If a lock is held for a duration, one thread can spin on one processing core while the different thread performs its critical section on another core. On multi-core computing systems, spin locks are widely used in many operating systems. Why don't we take a break here so that you can look over your notes and get a firm grasp on the mutex lock and so on. And when you're ready, come on back and we will proceed to the next topic, which is the use of semaphores.